Hello everyone, and welcome back to the podcast. I'm your host, ichino-ani, and I'm so excited to be here with you today. Today is May 11, 2026, Monday. I hope you are all having a fantastic start to your week, and that you are ready to learn something super cool today. Grab your favorite drink, get comfortable, and let us dive right into the fascinating world of machine learning and the human brain. Today we are looking at an absolutely amazing new paper from the arXiv. The title is When Brain Networks Travel, Learning Beyond Sight. The drill is, it is a bit of a long title, but I promise the ideas inside are super exciting and easy to understand once we break them down together. So let us talk about the big problem this paper is trying to solve. Imagine you are a doctor, and you use a special camera called ichino-ani to take pictures of the brain. These are not just regular pictures. They show how different parts of the brain talk to each other, which we call brain networks of functional connectivity. Doctors and scientists use smart computers, specifically graph neural networks, to look at these brain networks, to help find out if someone has a condition, like autism spectrum disorder or major depressive disorder. This works really well when the computer is trained and tested on pictures from the exact same hospital. But if you take that highly trained computer and try to use it on pictures from a different hospital, it gets very confused, and its accuracy drops a lot. Why does this happen? Well, different hospitals have different types of cameras, different scanning rules, and different types of patients. The computer gets a little lazy, and instead of looking for real medical signs of a condition, it learns to look for hidden clues about which hospital the picture came from. We call these clues sight wondershi, unconditional shortcuts. It is like taking a test and guessing the answer just by looking at the teacher's handwriting, instead of actually knowing the math. Also, traditional methods usually just take a big average of the brain activity over the whole time you are in the scanner. Our brains are not frozen. They're always changing, moving, and thinking. Taking an average is like looking at a blurry photo of a dancer. Instead of watching a beautiful video of the dance, you miss all the important transient neurodynamics, which are the quick changes in brain activity that hold very important clues about diseases. To fix these big problems, the brilliant researchers proposed a brand new system called CORE. CORE stands for Cross-Out Cut-Up Distribution Robust Brain Network. It acts like a very smart and patient teacher for the computer, and it is built with 3 very special steps. First, CORE does something called sight-to-orange confounder decoupling. This means it carefully figures out what the specific camera biases and demographic differences are for each individual hospital. Instead of trying to clean all the data with one giant broom, it uses a specific, tailored broom for each site. It uses something called Huber regression to estimate these biases and cleans them away. After cleaning, it looks across all the hospitals and finds a reliable scaffolded brain connections that are truly related to the disease, no matter where the picture was taken. Second, it does something called transient pathway profiling. Instead of taking that boring average of brain activity, it uses sliding windows to track how the brain connections dance and change over time. But because tracking all that dancing can be overwhelming for a computer, it summarizes these dancing patterns into neat, lightweight temporal descriptors. It measures things like temporal volatility, which is how much the connection jumps around, and dynamic flexibility. It organizes these connections into a line graph, so the computer can easily understand the pathways. Finally, CORE uses a preordained seguin adaptive mechanism. This is a fancy way of saying it perfectly balances what is normal for everyone with what is totally unique about you. It uses that reliable scaffold we talked about as a helpful guide, but it uses a special gate to allow the computer to focus heavily on the specific brain pathways that are most active and relevant for the individual patient. It suppresses the noisy connections and highlights the important ones. The researchers tested CORE on huge real-world datasets: paving for autism, rest method for depression, and AD for attention deficit hyperactivity disorder. And guess what? CORE did an amazing job. It outperformed all the older baseline methods by a lot, proving it could travel from hospital to hospital and still make highly accurate and robust predictions. Now, how can this super smart technology change a real, everyday world? I have 3 great specific application examples for you. Example 1. Reliable hospital diagnostics anywhere in the world. Right now, a fancy brain scan AI tool might only work perfectly at the big, rich hospital where it was invented, but with CORE technology, a small, rural clinic in a tiny town could use the exact same advanced AI tool, even if they have an old or completely different brand of fMRI scanner. The core system would automatically clean up and ignore the scanner differences and give the local doctor a highly accurate, trustworthy analysis of the patient. This means everyone gets top, left-guide and fast diagnoses, no matter where they live or what hospital they visit. Example 2. Massive global medical research collaboration. Scientists all over the world want to share their brain data to help cure big, complicated diseases like depression and autism. But normally, pooling data from dozens of different countries is a messy disaster, because the site biases and scanner differences ruin the combined data. With the core framework, researchers can smoothly and safely combine data from everywhere. The system will carefully decouple the site biases, allowing scientists to find true, universal patterns of brain disorders hidden in massive datasets, leading to huge breakthroughs much faster than ever before. Example 3. Personalized medicine and treatment tracking over time. Because Core is so incredibly good at watching how brain networks dance and change dynamically, doctors could use it to see if a specific medication or therapy is actually working for you. If a patient starts a new treatment for depression, the doctor can take it for you after a few weeks. You use Core to see the transient dynamic changes in the specific brain pathways. Since Core pays close attention to the individual subject through its adaptive gating, it can tell exactly if that specific person's brain networks are becoming healthier. This helps doctors stop guessing and allows them to choose the absolutely perfect, personalized treatment plan for every single patient. Is that not just wonderful? Technology like Core helps our computers understand human brains so much better, but it truly helps make the whole world a healthier, happier place. Thank you so much for joining me today and listening to my class on this brilliant machine learning paper. I hope you have a beautiful, productive rest of your Monday. Keep wondering, keep exploring, and keep learning new things every day. I am ichino-ani, and I will see you next time. Goodbye, everyone.